Log on, tune in, find out. Another good idea from Cambridge.
Because there is some things notation which I think I'd rather have on the slide, but I try to write as little as possible, and I hope it stays there and doesn't just disappear off. Anyway, so F is an infinite field. It has characteristic, prime characteristic, and so you have a vector space, and then you have a free Lie algebra generated by this vector space. So maybe I should, yes, and I was going to write down a little bit on the board to slow me down basically. So I'm talking about three classes of modules. The first one is homogeneous parts of the free Lie algebra. So LNV is, LFV is the Lie algebra generated by V, and LNV is contained in the tensor power V tensor n, and in fact you can write it down explicitly, and I should probably also write down the Lie brackets. So xy is what you think it is x tensor y minus y tensor x, and otherwise you don't put any relations on it, and then you can put it into homogeneous parts. So the homogeneous part is the part in the nth tensor power, and so you can explicitly write it down as that, and omega n is some element in the group algebra of the symmetric group. I'm going to write this down. Have I written it down here? Yes, I've written it down there. And yes, right. So how does this thing look like? So you have L2 of V, that's very easy. That's just the second exterior power. But if you have more than higher powers, then it gets complicated. And in general, Ln of V is spanned by, yes, you can take left normalized commutators, V1, V2, V3, and so on, Vn. So you put brackets here, and then this is sufficiently complicated, and it's quite a big thing. So okay, so then you have another module which you can get by applying the Schur functor to this Lie power, and that's a module of the symmetric group. And so this is slightly more friendly because you have a nice basis. So this has a basis. Okay, so you first start by fixing a basis of V. You can do that, and you assume it has dimension at least n. And then you can just take the left normalized commutators x1, x sigma 2, x sigma 3, sigma 3, and so on, x sigma n. And to get a basis, you take sigma in the symmetric group of degree n minus 1, fixing 1, right? 2 up to n. Okay, so you see from that it has dimension n minus 1 factorial, and you also see that it's free as a module for the symmetric group as n minus 1, right? Rank 1. So that's an interesting bit of information, but of course it gets big, and then if you try to calculate with this thing here, well, it's nice if you look at permutations which just fix 1, then it's just some permutation. But of course you have the transposition 1, 2, and that, of course, if you try to work out how this acts, you get into a mess. And so that's another module you like to understand. And the third one is, well, I probably won't get very far, not sure whether I do or not, but let me just write down how to think of the third one. It's actually much easier. Yes, right, so how do I do that? Can one move these boards? No, one can't move them. Okay. So okay, so can you see what if I write here on the bottom of this thing here, yeah? Right. Okay, so the third one, the best thing to think about it is you take an exact sequence and then in the middle you take V tensor the d minus 1 symmetric power of V, and then you have a map onto the d symmetric power. And yes, right, so then you see that this is actually a dual Y module. It's the nabla of partition d minus 1, 1, and so this might be another reason why this is interesting. But of course that's easier than the other three. Yes, right. So what happens? My slide has colors and there are no colors. What happens to the colors? Right, anyway, right. So, right, yes, motivation. So why would one want to look at these things? Originally, I started talking with Laci Kovac ages ago, and of course, he's a group theorist, and so this seemed to be a topic which is also interesting for group theorists, because you have nilpotent groups, and so it might tell you something about central series. And so, of course, then I looked up MathSciNet and typed in free Lie algebras. So on the 4th of September I had 525 hits for that, and it goes of course through a large part of mathematics. You have algebraic topology, and you have this Lie module occurs as homology for configuration spaces, and you have other places where it appears, and of course, usually it might appear over characteristic 0, but I think it's interesting to understand that for prime characteristic. And then you have algebraic combinatorics. So there's this book by Reutenauer, which is called the free Lie algebra. And yes, right. And then the search for new modules. And yes, right. I'd like to quote Ben Webster. So he said yesterday, well, the first thing you look at is you look for irreducibles, right? Well, he isn't here, right? Anyway, so he said that he said that yesterday, and of course you all know if you try to look for irreducibles of GLN over prime characteristic, you have quite a hard time. So if you don't know what the irreducibles are, then you might like to look at other modules and perhaps get some new perspective, right? So that's basically my motivation, right? Okay, so what do I do next? Press this one here. Okay, right, so yes, right. So let me just get back to this omega n element here. So it's known that if you square omega n, then you get n times omega n. It's not so difficult to calculate. And so you see from that, if the characteristic does not divide the n, then you almost have an idempotent if p does not divide n. It's almost idempotent. And so that tells you that in that case you have a splitting. And so the LNV is the direct summand of the tensor power, so it's a direct sum of tilting modules. And even if p divides n, then you still have summands which are tilting modules. And so as a first approximation, you might ask which tilting modules appear there. And I suppose we have heard this morning that finding characters of tilting modules is a hard problem because it's the same as BP3, yeah? And so anyway, of course we're not asking what the character of a tilting module, well, we can still ask it, but we won't be able to answer it. But we can ask which tilting modules occur. And so we can look at classical results. So Klatschko in 74 answered this for characteristic 0. So if the characteristic is 0, then the tilting modules are just simple modules. And so he's proved that almost all occur as submodules or summands. And last year, Roger Bryant and Marianne Johnson have proved a Q analog of that, a P analog of that. And in the P case, of course, you wouldn't ask for simple summands because there won't be any, but so you would ask for tilting summands. And so it's again the same, that almost all tilting modules occur as summands. And so we finished it off in the case when the dimension of, R is the dimension of V. Yeah. When the dimension is 2, then of course you have a lot more tools, then you can do some more. So anyway, so that's answered, which is sort of discouraging, because what you really like to know is modules, new modules, and tilting modules aren't really new. So, right, so what do you do? Right. Okay, right. Okay, so this tells us something about tilting summands. So you can write L of V as a part which is a tilting summand. Maybe call it tilt. And some part which is not a tilt, Ln V, which is tilting free, TF. And really the interesting thing is, what is this one here? And similarly, you can write Ln as a projective part. Ln projective free, right. And so you have the same thing if P divides N, then of course this thing here is idempotent again, and this is everything, but if P does not divide N, then you have some other things, and these are the interesting modules, right. Okay. Right, so what next? Yes, right. So anyway, so we were discussing these things and trying to find summands which are not projective. And yes, right. And so we were playing with these things and not knowing what to do. So we looked at block components, and well, for block components, it's convenient to look at symmetric group modules, because there you have blocks. And yes, right. So we split this Lie power into blocks, and then ask what are the block components. So as Radha told us this morning, is that blocks are parameterized by p-cores, and p-cores are partitions, and there's a principal block, the block of the trivial representation, and this has empty p-core. And so we proved that if we have a known, okay, so I should also say, okay, Tan, so Kai Meng Tan, I should mention that he was in Cambridge as an undergraduate and also as a graduate student, yeah. Maybe you remember him. You remember him. Yeah, right. Okay, anyway, so we worked on that last year. Anyway, so, okay, so we take a block component, and so we ask, what can we say about this block if this does not have a projective summands? And actually, this is a fairly easy argument, just a few lines, and I'd like to give this argument and tell you about the proof, because every lecture should have a proof of some sort. Yeah. Okay, so let me give you the idea of this first theorem here. So you take a module with summand of Lie n which is not projective, and it lies in a block B, so it lies in Lie n B, and you'd like to know something about the block, right? So Q, the block has a defect group, so Radha has explained defect groups as well. So Q is the defect group. And well, you don't really need to know much about it. You just need to know that M is relative projective with respect to this defect group. So M is the summand of, if you restrict to Q and then you induce up again, Sn. Yeah, I don't know whether you said that explicitly, but it's easy. Right, so okay, so if M is not projective, then M restricted to Q is not projective, because otherwise M would be projective. And so M restricted to Q is not projective. Right. So we have just seen that, well, we have seen at the beginning, I've said it, that Li n restricted to Sn minus 1 is projective. So M restricted to Sn minus 1 is projective, because it's a summand. And so Q cannot be a subgroup of Sn minus 1, yeah? So Q is not in any Sn minus 1, any conjugation or whatever. And so, right, so then you have to remember what Radha said, namely that Q is a Sylow subgroup of Sn minus size of the core, kappa is the core. I think you did say that, did you? Yeah. Right. So Q is a Sylow subgroup of some symmetric group, but it's not contained in Sn minus 1, and so this tells us that the core must have size 0, right? And so the core must be empty. And therefore the block is the principal block. Yeah. Right. So that's a fairly simple-minded argument. It's sort of surprising that nobody has looked at it. Anyway, so here it is, and so you translate it by using Schurfunktor to LNV, and then you get the same thing. And the projective modules for, if you look at GLV modules, and here you have symmetric group, you have the Schurfunktor, Sn, Fsn. So here you have a projective module, projective d lambda, so this one is projective, and this corresponds to the tilting module t lambda under the Schurfunktor. And so if you translate it, then you get the same statement for LNV. So if you have a summand which is not a tilting module, then it must belong to the principal block of the Schur algebra. Well, it might not be a block, but a class of blocks, yeah, right. Yes, right. And I probably should stress the point that here the symmetric group technology actually gave some new things for JLV, which wasn't known before. And I don't know whether you can do it directly. Okay, right. So then you might ask, what can you say about the structure of the components which are not principal block? And yeah, we have some surprisingly some closed form for that. So you take a block which has core kappa, and kappa is not empty. Then we know that Li NB is projective. So question, how does it look like? And yes, right. So what did we do? Basically doing character calculations. I suppose I don't like characters in general, but here it was rather interesting to do. And now I'm including all this chalk. Sorry, this wasn't a good idea. Yeah, I have to use such microphones for my undergraduate lecture, and there the problem is that the battery is usually empty in the middle of the hour. So here have a different problem. Right. Okay. Right. So what is this thing here? I should say something about the notation there. So yes. Right. So what do we mean by saying 1 over p to the m? So we mean that, okay, so Lie NB is projective. It's projective. So we take summand of that, and then what it means is that for every summand, this multiplicity is a multiple of p to the m. And so if we work out what the multiplicities are, then they are the same as if we take Lie k and we induce it from some subgroup, right? So what is this sk star? So n is p to the m k. So what we can do is we can take n into blocks of length k. So we have k. So we have lots of them. And so on each block there is a symmetric group sk acting. So we have the direct product of these things, sk and so on. And so in this group we have a diagonal sitting. One is a group sk which acts the same on each block, yeah? So this is a sk star is sort of the diagonal. And so this will be a subgroup of Sn. So, well, if it's isomorphic to Sk, then we can view Lie k as a module for this diagonal group and induce it. And then if we induce it, then we get the Lie NB. And I was going to say a little bit about the case when n is just p to the m, and because then it's actually an easy argument again, which I'd like to give. Yes, sorry, there's a typo on the slides. It should be n equals p to the m, right? So n equals p to the m. So what does it say then in this case? Then this k is 1. So Lie k is just trivial, just the identity. And so we induce the identity to the trivial module of the identity, k, f, to the symmetric group, and then we just get the group algebra of the symmetric group, and so it tells us that Lie p to the m is just 1 over p to the m times, yeah, so we take the block component of the group algebra, so it's just b, yeah? So that's what it is. So it looks very strange to me, but anyway, this is actually easy to prove. So here is the proof. So you need to know what the character of the Lie m is, which is known. It's liftable module, so it has a character. And so you can work out the inner products with some ordinary character, chi lambda. So you can work out what this is. You get 1 over p to the m. Then you get sum all divisors of p to the m. Then you take the Möbius function. Yeah. Right, and then you take the character value of lambda on sigma p to the m over d. And sigma is a p to the m cycle. So that's what you get if you write down the characters. Right, and so now if d is the divisor of p to the m, then nu of d is almost always 0, yeah? So you just get 1 over p to the m, then you get the degree, and then you get only one more term with a minus, and here you get sigma p to the n minus 1. Yeah, right. So, yes, right. And so the thing is, this one really just says that this is always 0 here. And so the question it's not always 0. It's 0 provided if the p-core of lambda is not empty. Yes, so if you teach symmetric groups to undergraduates, you've probably seen the Monaghan-Nakayama rule, yeah? Has everybody seen the Monaghan-Nakayama rule? Then you see that, okay, what you do, I mean, you have to take, remove hooks of length p, because this thing has this one here has cycle type p, right? P, and so on. So to calculate the character values, you have to remove rim p hooks of length p until you can't do it anymore. But if the p core is not empty, there aren't any sequences like that. So you get 0 here. And so this is 0 here, and so you just get p to the m times character value of 1, and this just tells you that here, basically. Right. Okay, good. No more proofs today, right? Okay, so yes. Okay, so then of course we'd like the character of this component. So the question is, what is the character of this module in general? And then you have a formula for this. And it looks almost like that here, except that there is a borrowed character appearing, and you have, it's called Tor there, because it's not a p cycle, but it's one of these diagonal cycles. And yes, I should probably also say here that this is very nice, but of course beta lambda is not known in general, so it is a formula, but of course you have some items in it which you don't know. Anyway, so when you take the case k equals n, so this is the case when p is not dividing the degree, then this recovers the formula which Steve Donkin and I proved some years ago. And if you have characteristic 0, then you get the same formula, but the usual character here, in fact it's just this one here. And so this was proved in the 1940s I think by Weaver first. And again, you can translate this to Lie powers, and you get this block decomposition. You get okay, so the first bit was writing Lie n as an induced module. This becomes writing lnv as the kth Lie power of a tensor power, and then you have a character formula. The multiplicity is exactly the same, yeah. Right, so what did I want to say? Yeah, I think I don't want to say anything for that, and move on. And yes, right, going back a little bit in time-wise, but there was a theorem proved by Roger Bryant and Manfred Schocker, which they called a decomposition theorem. So they reduced the question about Lie powers to prime power degrees. And so they have this formula, so they take lnv and they write it as direct sum of lq of b. So q is the power of p, and this b appearing is always a tilting module. And so in some sense you could say, okay, if the degree is not a p power, then this tells you perhaps all you want, as long as you know what happens for p powers. Right, and so of course you can then translate that forwards or backwards to symmetric groups, and you get a formula. So this was proved by Karin Erdmann and Kei-Jin Lim, which the people from Aberdeen might remember. Right, world is small, yeah. Right, so I should say something about this notation, what this actually means. And from the group representation theory perspective, the crucial things are Riesz products appearing here. So you have n equals q times t, I believe, and q is the p power. And so you look at a group which is a Riesz product, St with this q. So this has a base group, of course, again, ST cross ST and so on. And then it's a normal, then you have SQ acting on it. Right, so that's the group. So what modules do you have for that? So if you have a module for ST, so if X is a module for ST, then you can take the tensor power of that. Well, this is of course a module for ST in the diagonal action. If you take the, if this base group here, but it's also a module for the Rees product, maybe call this H for the moment. So this is also an H module, because you can let the base group just act as it acts anyway, and the top group here acts by permutation, yeah? So this is a module. You have to check that this actually works, and it does. And so this is a module, and then you take any module for SQ. So for example, you can take LQ. This is an SQ module, but you can view it as an H module by just inflating it, right? Can be viewed as an H module. And then you can take the tensor product that's done here, which is just the usual tensor product, and you induce it, and that gives you a description of this new module. Right, okay. And note that this xt is actually projective because it's the image under the Schur functor of some tilting module. Right, okay, so what do you do with that? Yes, I mean you have lots of applications. One thing we did is we estimated complexity. So complexity of a module is the rate of growth of a projective resolution. And so a question is, how can you study rate of growth of projective resolutions if you have modules for Rees products like that? And we can do that. And there are some other applications, but I don't want to go into details because you don't want to. Right, okay. I have some more applications. But now then all these things suggest that degrees, prime power degrees, is really the most interesting one. And so question is, what can you say about prime power degrees? And of course, it's the same thing. You would like to know L p to the m v, and this, I mean, you have reductions to these things, and that's of course what you would really want to understand, and that's where the main problem lies. And yes, right. So okay, so the first thing you might do is look some small examples, and so you can do Li p. PF projective, oh yes, right. So I've rubbed this off. So what is this PF? So of course we always have this decomposition into projective part and projective free part. So we really want the part which has no projective sum ends, right? And this is the non-tilting part, right? So that's what we like to know. And yes, right. So you look at small examples. So Li p, this is not very difficult, and yeah, right. So what you get is you get the Heller translate of the trivial module. In fact, it's also a Specht module if you want, but that's easy. Then you could look at Li 4, which you can also do by hand, basically. Maybe I should say a little bit about how you calculate Li 4. Just to give some flavor of what you can do. And what you can't do, of course. Right. So you have Li 4 here. So you have an exact, so this is an S4 module, and the characteristic is 2, right? And P is 2. So what you can do is you can show that there's a surjective map from if you induce Lie3 from S3 to S4, and then you have some kernel here, don't know what it is, call it U here. So there's an exact sequence like that. So Lie3 is something which is, yes, exercise, ask question for the audience. So what's the dimension of Lie3? It should be 2 factorial, which is 2. And so how many modules of S3 with dimension 2 you have? And well, you don't have so many. S3 is a very small one, so you just have S21, Specht module of S3, Specht module, and this is in fact projective. And so this thing here is projective here, and what you can check is that this is isomorphic to the projective cover of D31. It's not hard to see if you induce the Specht module to S4 that you get this projective, yeah? Yeah, right. And so then you count dimensions, so this has dimension 4 factorial, 3 factorial, which is 6. So this has dimension, yeah, what is the dimension of that? It's 8, yeah? 8 dimensional. And so this one is therefore 2-dimensional. And yes, right. So a 2-dimensional submodule of this projective, it's just a simple module here, yeah? It has to be this simple module. And so this is therefore omega inverse of this simple module. So here you are lucky, it's small enough and you can actually play around and get an answer. But then of course, if you have larger degrees, then these things get very large. And I have written down what these dimensions are, some dimensions. Anyway, so just to say what is on this slide. So anyway, Susanne Danz and Jürgen Müller did some computer calculation, and not just that, some ingenious guesses. And so they got answers for degree 8 and prime 2 and degree 9 prime 3. And just to give you some numbers, so if p to the m is 8 and prime is 2, so how large are these things? So the dimension of Lie8 is of course 7 factorial, but the projective free part has still dimension 816. So it's too big to do much by hand, but the computer can deal with that. So they calculate the vertex of that. And the vertex is a regular elementary abelian of order 8. Yes, I was wondering whether I should just remind people what a vertex is. I think you haven't used vertex. So it's a minimal subgroup. So what is a vertex of an indecomposable module? So it's a minimal subgroup D in G such that M is relative D projective. M is relative D projective. So M is the summand of M restricted to D and induced to G. And then you also have a source. So a source is a D module, indecomposable D module. And you can get M as a summand of S induced. M plus something. Right. So okay, so in some sense the vertex in the source will give you main information about how to get hold of your module. Anyway, so they calculate a vertex, regular element abelian of order 8, and they also have a source, and that's why I asked Jeff about endopermutation modules, because the source turns out to be an endopermutation module. And yeah, what is an endopermutation module? The so M is an endopermutation module I hope I get it right, endopermutation EPM, if the module M tensor M star, the dual, is a permutation module. Yes, is that right? Yeah. Well, it doesn't quite tell you why it's called endopermutation module, but M tensor M star is isomorphic to the K endomorphism ring of M.
Permutation module for the K, just for the whole group.
Well, of course, you can define it in general, but I mean, of course, you would here look for P groups, yeah. And so the source in that case is an endopermutation module. And well, this was introduced by Dade, and he actually classified endopermutation modules for abelian P groups. And fortunately, this is an abelian P group, so you actually can identify the isomorphism type of this source here. And so what is it? So the source in that case is what you take is omega to the 3 of f. Then you take a big tensor product over all subgroups of order, we call it E8, over all subgroups of order 2, and you take omega inverse. No, you take the inflation of omega inverse of the trivial module of this factor group, E8Q. So you can write it down. And, well, it's not quite right, because this could have projective summands, but modulo projectives, it's just that. Projectives. Right. So this was a surprise to me, certainly. And, I mean, first thing, I was really surprised that they could actually, or probably just Susanne this bit, that she could actually find what this thing was, and then, of course, the answer here is quite strange. Anyway, there's a similar thing for 9. They also did the calculation. The vertex is a regular elementary abelian subgroup, and the source is again an endopermutation module. And yeah, right. Well, that's great, and of course then you think, well, maybe this should be true in general, and so question is that always the case? So is the part which is not projective indecomposable, is the vertex regular elementary abelian, and the source an endopermutation module. However, we've looked at that for several months, and we don't really know how to get hold of that, because the computer calculations have reached the limits, and we don't know how to do that. So I thought it was a good thing actually present that here. Maybe somebody has some suggestion what to do. And then, okay, so in the search of new modules, then, of course, there is one obvious two questions. One is, these are just sources, so then the question is, if you induce these things, you get lots of stuff, lots of summands. So what are actually the module itself? Yeah, so you have some G module which has the source. What is it? And then, of course, you have a question: is what is the analog of this? What is the correspondence of this? What corresponds on the GL side to these endopermutation modules? Corresponds on the GLV side to the endopermutation modules. So I think this is actually a rather interesting question, and I think there are new modules, and I don't know what they are. Of course, there must be there, because if you take the L8 of V and apply the Schur functor, then you get these things. Yeah. So there must be some summands which correspond to that. And so what is it? And I don't know. Right. So. Right, so this is the analog for GLV of an endopermutation module. I mean, I can say what it is for L4 of V, but not, that's the only one I know. Right. So this is about all I wanted to say about Lie modules of symmetric groups and of GLV. I should just spend a few minutes on the Metabelian Lie power. So I have already said we take this exact sequence. It's gone, right? It's gone, right? Yeah. Sorry, I should be careful and not knock the microphone again. Right. So we have this exact sequence. We take symmetric powers and tensor take this exact sequence. Take SD. So SD of V is just the dual Weyl module labeled by partition D. And then, so therefore you have SD Weyl module there and some tensor product of two Weyl modules in the middle, and therefore the kernel must be again, it is a dual Weyl module. And the submodule lattice of SD was studied long time ago by Doty, Kopp and other people. And of course this is multiplicity free, because even the weight spaces are multiplicity free, and you can write down a submodule lattice. And in fact there's also a Q analog, so I think somebody from Aarhus has calculated the Q analog of that. And yes, right. And so it has a so-called P-good filtration. So Donkin introduced at some stage the term P-good filtration. Yes, sorry, I forgot to say that lambda should be P-restricted, right? P-good filtration. So every quotient should have a quotient of the form L lambda tensor some other dual Weyl module twisted, and mu should be P-restricted. The lambda is P-restricted, right? And so for symmetric powers you can describe it nicely. So if you have a symmetric power, Sm, you have a submodule, what can you do? If m is not too small, you have a submodule V twisted, or takes p powers, and then Sm minus p. And then you factor this out. Here you get a module which we called Sm bar, and this one is simple. So basically you take cosets of monomials where all degrees are at most p minus 1, yeah? And so that is simple, and it has highest weight p minus 1 a b. If m is a p minus 1 plus b periodically, and b should be less than p minus 1. And so you get a p filtration. The quotients are just of the form Sm minus p kp tensor Sk twisted. And so this is again a dual Weyl module, so this is nabla k twisted, and so this is a simple one. And so you have p filtration, p good filtrations, and we get also p good filtrations for the MD, and it looks very similar. And so what you do is you take the p-good filtration of SD, and you also have one in the middle there, and so you basically take the one in the middle and intersect it, you get a p-good filtration of MD. And so we construct it explicitly, and we also find composition factors, highest weights of these. It's not so difficult. Anyway, and then you see it's multiplicity free, which is not so obvious here because the weight spaces are not one-dimensional anymore. And yes, it has some history. So after we looked at it for a while, then Lazzi found this paper by but Turin, which is in Russian, of course, no chance to understand it. So he has looked at this submodular lattice in a different language. So he looks at varieties of the algebra. And so, I mean, yeah, I mean, he has the answer of the complete submodular lattice. It's distributive as it should be, of course. But of course, he doesn't have composition factors, and it's of course hard to read anyway, even if you can speak Russian. So anyway, one thing to remark is that we don't need any conditions on primes, so it works globally. And I think generalization to dual Wien modules with hook partitions is probably feasible. And yeah, right. So if somebody wants to do it, can do it. I should also mention that Steve Donkin has this conjecture that every dual Wien module should have a p-good filtration. There's a paper by Henning Andersen where he has a proof, however, the proof is not complete, so it's open in general. So at least it's not a waste of time, right? So I think that's probably about all I wanted to say, so I should probably stop. Thank you for your attention.
Thank you. Other questions? Doesn't seem to be the case. Then let's thank all the speakers this afternoon.